Hi, it's that time again. We have to go over your quiz corrections. So let me help you. We're going to do numbers 1, 2, 3, and 4. We'll do the front in one section and then we'll do the back too. And I will try and keep it to less than 10 minutes apiece because I know it's hard to sit and listen to me for that long. So that said, if you would please join me. The very first one on your fluid systems quiz talks about, here we go. We have fluid systems may be open or closed. So the first thing you should be thinking of is, oh, I know what an open system is and I know what a closed system is. Many mechanical systems are modeled after natural processes. What that means basically is a lot of the things that we use are based on things that happen in nature. Explain, please. That means you need to use all of your nerdy knowledge in order to fully explain this. Which human body system is like a closed system that contains a liquid? All right, so closed system, first of all, is one with no leaks. Okay, so nothing can escape. So you want to think of some part of your body where nothing escapes. All right, and something that uses a liquid. A lot of you I saw put down veins. That's great. You're right. Your blood is contained inside of your veins, your arteries, all of those things. Some of you use the biological term, which is the circulatory system. So that is an excellent one. So veins, circulatory system. Or your blood, you could say that too. They are a closed system because nothing leaks. All right, and it contains a liquid. All right. All right, so those are all great systems to use. That said, I think I spelled veins wrong. I think it's V-I-E. V-I-E-N-S. I don't even know. That's kind of embarrassing. I should probably look that up. Anyway, that is one example. I am going through and taking a look at other systems that could possibly also be closed systems, so it will be left open to interpretation. But that is one of the ones where nothing escapes, and that's the thing. There's no leaks. That's what makes it a closed system. That said, an open system is one where things can get out. They can leave the system. So that is what you use in your explanation. This is an open system because things can leave. We also want to contain a gas. I know a lot of you talked about the flatulent system, so I got a lot of butt jokes. All right, and actually, when you eat, you do ingest some gas, which is why sometimes you burp, and sometimes you toot. And all of those things are open systems because there is gas leaving the system. Another one that's really good that I saw are the lungs, or the biological term is respiratory. I saw some of you knew that. Respiratory. I gotta do some respiratory system. I need to go back and study my biology. The respiratory system, all right? So again, you're saying the human body function, butt, burp, toot, lungs. It's an open system because things can leave and they function using a gas, okay? So there you go. Each one of these are going to be graded out of 4, okay? So what I'm looking for is that you have all of these things. You have the system identified, you have told me why it's closed, and you are using a liquid, all right? So that's going to be graded on a 1 to 4 scale. Same thing here. You are telling me which body function, why it's open, and if it contains a gas. You're using a gas, all right? So that will get you your points for that. Moving on, number 2 is asking you that you have a closed fluid system again. Okay, a liquid exerts a force. Oh, we have a force. That's good. If you notice, this is easy because it tells us on a piston. A piston is like the pump on the end of your syringe, so it pumps up and down. With a cross-sectional area. Love that word. Love it. of 12 square inches. So that right there is our area. That's excellent. Okay, so we have some information. Calculate. Oh, I love calculating. Calculate the pressure. I can do that. Great. Of the liquid in the system. Show your calculations. You have to. Include your units. It asks you to. Please make sure these things happen. All right, that said, if I want to calculate the pressure, my pressure equation is force divided by area. The nice thing is that as I went through, I just made sure that I was labeling everything. I have a force and I have an area. So let's do this. Pressure is force divided by area. My force is 360 pounds. That's including my unit. You don't drop that. Just like in algebra, you would not drop your x's and y's. You don't drop your units in physics or in science. All right, my area, 12 square inches. You can also say inches squared. All right, those two things are the same. When you do 360 divided by 12, 36 divided by 12 is 3. Add your 0, you have 30. Or use your calculator, that's fine. When I take a look at my final unit, you notice here nothing is being divided by itself, which means you have to write everything out. Pounds per square inch. That is your total final answer. Now, I'm giving you 1 point for making sure you write the right equation, 1 point for substituting it in correctly, 1 point for getting the right number, and 1 point for having the correct unit. So again, that is going to be scored out of 4. Great. This one's kind of challenging, and this is a very MCASI question, so I want to make sure that you understand how to do this. Wind blows around a skyscraper at high speeds. Okay, that's velocity. Oh, the air pressure outside becomes lower than the air pressure inside. Great. Do you know what they're telling you? They're exactly telling you Bernoulli right here. If Bernoulli's principle was not considered, what could happen and why? So we need the what and the why. Now, Bernoulli's principle is outlined exactly for you. They say there's high speed, the pressure becomes low. The air pressure inside is high. So that means that if there's low speeds in there. So we know this because with Bernoulli, your velocity, when it increases, your pressure decreases. Let's draw a little picture really quick. What they're saying is you have this building. Here's our building. Whee! Let's make it three-dimensional. Look, it's an isometric drawing. Yay! Now we have the wind blowing, so we have very high velocity outside, but that means we have very low pressure. Inside we have very big pressure because the velocity is much different. Remember, whenever you have two different pressure systems, your higher pressure wants to go to your lower pressure. So if you don't take Bernoulli into account, what's the stuff that's going to be happening? What's going to be pushed when your higher pressure tries to escape to the lower pressure? It's going to be the windows. Could pop out. And that is because the high pressure, so we've done what? High pressure wants to go to the lower pressure place, wants to escape. All right, so now we've done the why. Higher pressure moving to lower pressure sometimes is a really good thing because it can provide lift for an airplane. In a situation like this, blowing the windows out of a building, that is not a good thing. So we don't want that to happen. Again, I'm going to grade that out of 4. So the what is going to be half of it and the why is going to be the other half. All right. Here we go. The last one for this side, and then I'm going to pause it so that you guys can move on to another video if you don't need to do these. Air currents. All right, so we're moving our fluids again. The air move faster. Oh, okay. That air currents above the bridge. So under is moving faster than above. Okay. We're doing Bernoulli again, where we have a faster air. That means we have a bigger, no, we have a smaller pressure. Sorry. Bernoulli says higher velocity, smaller pressure. Sorry. So below we have low pressure, and above we have high pressure. Again, we can just go ahead and draw this. Here's our bridge line. The bridge is falling down. We have little pressure here. We have big pressure here. That said, let's see what the question is asking us. Which of the following explains the result of Bernoulli's principle in this situation. Air currents under the bridge exert less pressure than air currents above the bridge. Oh, there's less pressure under than there is above. Okay, so we kind of wrote the answer. Well, that's awesome. I haven't done this yet, sorry. Okay, so yes, that could be one. Great. Air currents under the bridge create more condensation than air currents above the bridge. Oh, well, Bernoulli doesn't have anything to do with condensation, so it can't be that one. Air currents under the bridge result in greater air volume than air currents above the bridge. Bernoulli doesn't talk about volume, it talks about pressure, so it can't be that one. Air currents under the bridge cause a lower temperature than air currents. Again, Bernoulli doesn't talk about that. So we really only have one option for this because there's only one thing that talks about the velocity and the pressure. Okay, great. I'm going to pause this so that we can go on to something else.